Okay, so today we'll continue on the chapter of Hamiltonian mechanics, right? So last time we haven't really actually get into the point of Hamiltonian, right? So, but what I did is just introduce this mathematical procedure, which is known as the Legendre transform, right? Is that suppose we have a function, right? So in this example, that we have this function of two variables, okay? And then the Legendre transform is that if I want to basically change, okay, so the how we represent this function, right? So instead of writing it as fxy, we write as guy, right? So and then this procedure, right? So is known as a Legendre transform. So you see that instead of writing as fxy, so we write a guy. That means this one variable is changed, right? So from x to u, okay. And this u and this x, okay, so they are actually related, okay. So they have to be related by this relation here, right? So if you do Legendre transform, right, so this has to be satisfied, right? So and the g is written as this ux minus f, okay. So before we move on, so I want you to do one small exercise here, okay. So just to refresh our mind, okay. So here I give you a function, okay. So and then I want you to try to do the Legendre transform, okay. So the function that I'm giving you is written like this: f of x and v, which is given by 1/2 mv squared minus 1/2 kx squared, okay. So this is function of two variables, okay. So f x v, and then I want you to do a Legendre transform and give me a function that is g x p. So you see that the v is replaced by p, right? So and when we do that, right, so you understand that p has to be given by partial f partial v, okay. So try to spend a couple minutes to do the Legendre transform for this function here, okay. So this function, right, so when you look at it, okay, so you might recognize that it basically is the Lagrangian of a simple harmonic oscillator, right? So however, at this moment, okay, so I want you to be not worried about what this is, okay. Just forget the physical meaning of this function. Just treat it as a mathematical function of two variables, and then just follow the exact same procedure, okay. So to give me this g xp, okay. So try to spend a couple minutes on this. Okay, so we know that the f and g is related by this, right? So this is easy to remember actually, right? So because the first term, right, is the product, right? So of the original variable that you are trying to get rid of, right? So together with the new variable, okay, and then this term minus the original function. Okay, so then first of all, let's figure out the p, right? So over here, right? So p is this partial f partial v, right? And you can easily see that this is just taking the partial derivative for the first term only, right? So and this is simply m times v, okay. So then the G would be M times V minus F, right? So F is over here, right? Just that. And that would be 1/2 mv squared plus 1/2 kx squared. Okay. Okay, we are not done yet because G is a function of x and p. Okay, so now we need to get rid of the v and replace it with the p, right? So, but from here, right? So we know that v is just p divided by m. Okay, and that means 1/2 mv squared is just p squared divided by 2m, right? Right, so then this is the G. Okay. So, well, I told you to not to worry about the physical meaning yet, but anyway, if you look at this, right, so you recognize that this is a Lagrangian of the simple harmonic oscillator, and what about this? What does it look like? It looks like the total energy of the simple harmonic oscillator. Okay. And I'll come back to this. Okay, so but anyway, this is the mathematical procedure, right? So that we have learned last time. Okay, so and this is the example that we did last time. And then this slide, I think I'll just skip, but just when you, okay, so go to learn thermodynamics. I think there's a 3000 level course on thermodynamics. Maybe some of you are taking this. Maybe some of you will take it next year. Okay, so but when you learn thermodynamics, right? So and you realize that there will be different functions that will be defined, right? So that we usually call them the thermodynamic potential, right? So we have the total energy U, and then you learn something that is known as the enthalpy H, and then you also learn something that called the free energy F, the Helmholtz free energy F, and you also learn something called the Gibbs free energy G. Okay, so these are the different thermodynamic potential. Okay, so and then you realize that you can convert one from the to the other, and by using the Legendre transform. Okay. Okay, so now what about more variables? Okay, so for example, if I'm going to have this function that has let's say 4 variables. Okay, so a function again f that depends on x1, x2, y1, y2. Okay, and then by doing the Legendre transforms, okay, so I suppose I want to get rid of 2 of the variables, so x1 and x2, and then at the end I want to get to this function g, which I call u1, u2, y1, y2. Okay. So how does the Legendre transform work in this case? Okay. So in this case, the Legendre transform is written like this. That is, this G will be given by, if I'm going to just replace one variable, right? So I'm just going to have a term up front, which is x1, u1. So now I want to replace the other variable also. I actually just add one more term here. Okay. And then the whole thing, okay, subtracted by f. Okay. So, and again, u1 and u2 are related to x1 and x2 by this. Okay. So again, you can see that this is not difficult to remember this formula, as I said, right? So just take the product of the variable that you are trying to get rid of, okay, with the new variable, right? So that's why I have this x1 u1. Okay, and then now you have to add another term, which is the second variable that you are trying to get rid of, and the second new variable, which is x2 u2, and then the whole thing minus f. Okay. So let's verify that it works, right? So if I want to consider the total differential of g, which is dg, then what do I have? Then I would have this d, this whole thing, minus df, right? And well, product rule for the first term here, then you get a total of 4 terms, right? So u1 dx1 plus x1 du1 right? And then the whole thing minus df, right? So again, df, you will have 4 terms, right? So the partial f, partial x1 dx1, partial f, partial x2 dx2. Right, like this. So, and now notice that this term, you cancel this term, right? Because u1 is partial f, partial x1. Right? And then this term here will cancel this one, right? So then at the end, right? So we only have 4 terms. So that is like this. And you can see that now this dg, right? So has 4 terms, and which for the 4 variables, right? u1, u2, y1, and y2. And so now g is a function of u1, u2, y1, and y2. Okay. And again, if you consider using the definition of the total differential, right, for dg, right? So you know that this is right. So and then you can also find these relations, right? So this is equal to this, x2 is equal to this, right? So minus partial f partial y1 is equal to this and this. Okay, so you can see that it's straightforward to generalize this Legendre transform to the case where you want to replace multiple variables. Okay, so and essentially, right? So what I'm showing you in this slide is the case where I have this 2 n variables, and then I want to replace n of the variables. Okay. Okay, so now it's time to really apply this procedure to the topic that we care about. Okay, that is the Lagrangian. Okay. So what I'm going to do is to apply this Legendre transform. Okay, so to this Lagrangian and generate a new function that we'll call the Hamiltonian. Okay. So I'm going to start from, again, the simple case where I just have one generalized coordinate, right? So because as you said, as you see, it is straightforward to generalize it to multiple variables. So I have this Lagrangian for one particle system, right? So just with one generalized coordinates like this, okay? And then Legendre transform to give me this function that I call H, as I said, the so-called Hamiltonian. Okay. And I'm going to use this transform to get rid of the variable Q dot. Okay, and then replace it by a variable that we call P. Okay, like this. And then, right, so P has to be equals to this. Okay. So now, first of all, if I don't care about the physical meaning, right, so I can still do everything here, right? So nothing's wrong. Okay. So, and the P is just the name of the real of the new variables, right? So that is given by partial F partial Q dot. Okay. But of course, on the other hand, we already have the knowledge of Lagrangian mechanics. Okay, so we know that the P has the physical meaning of generalized momentum. Right? So that's from the physics. Right. So, but at this point, okay, so let me just forget about the physical meaning for a second. Right. So the whole procedure here is still a pure mathematical operation only. Okay. So just a new variable is called P. Okay, so now, right, so what would be the dH, right? Again, the dH would be, well, using this over here, would be P dQ dot minus Q dot dP minus okay. And now, right, so as we have required, right, so this one is called P. Okay. So then you realize that, again, the first term will cancel the last term. Okay. Oh, sorry, this should be a plus sign here. Okay. So then at the end, this is what we have. Q dot dP minus partial L partial Q dQ. And again, if we consider the total differential of dH itself, dH is partial H partial P dP plus partial H partial Q dQ. Okay, so therefore, right, so from this, I got this two relation, right? So this is the Q dot has to be equals to partial H partial P, right? So because of this. And then this partial L partial Q has to equals to minus partial H partial Q, right? Because of this. Okay, so everything just follows the same procedure as I taught, right? Now, we need to insert, okay, so the physics element into this. Okay, so what I mean is that, as I mentioned already, right, so this P, we know that this is the generalized momentum, so-called, right? And why do we call that the generalized momentum? Right, it is because of the Lagrange equation, right? So from the Lagrange equations, we have the following. Okay, so now let me have the physics element, right? So into this, right? So from the Lagrange equation, so this is what we have: partial L partial Q minus d dt partial L partial Q dot equals 0. Okay. And then when we learn about the Lagrangian mechanics, right? So we call this P to be partial L partial Q, right? So and then that means, right? So this ddt, I'm sorry, partial L partial Q dot Q, right? So and that means this partial L partial Q from the Euler-Lagrange equation would be equals to d dt P, right? So and which is P dot. So now, if you use this to plug it back to this equation here, okay, and then we get a pair of equations, okay, so which I want to write them out again, which is this one. Okay, so these pairs of equations are known as the Hamilton's equation of motion. Okay, so this is the important result that we'll use a lot. Okay, so in our examples problem. Okay, so to see how the whole thing works, okay, follow the logic. Well, first step, right? So the Lagrangian, right? So the pure mathematical procedures, right? So define a new function h, right? So we get to this function h, p, q, and p, and then we get to these two equations. Okay, so up to here, right? Pure mathematical procedure, and then we insert the Lagrange equations. Okay, and then this one is written as this one. Okay. So now these two equations, as you can see that what do we have? We have this Q dot. That means that this is telling us what does it tell us? The kind of the velocity or the generalized velocity of the particle, right? And then this one is the time derivative of the momentum of the particle. Okay. So examples will come later. Okay, so but these tools are called I hope that at least you're convinced that these tools are equations of motion, right? So of some form, right? So they can tell you the motions of your particle. Okay. So these two slides, okay, so basically summarize what I just written down here. Okay, so but here I clearly tell you that, okay, which step is the math, okay, which step is the physics. Okay. So one more thing here is that if I have a case where the Lagrangian depends on time explicitly, okay, so remember in the example that I just gave you, okay, so L is just Q and Q dot. Here, if it depends on this Q dot and also T, okay, so you have to consider the one additional term over here. Okay. And from here, actually, you conclude that the partial derivative of L with respect to time is equals to the partial derivative of the Hamiltonian with respect to time, just off by a minus sign. Okay. And also the total derivative of the Hamiltonian. Okay, so here you just really apply the chain rule. Okay, so also with the Hamilton's equation that we just derived, okay, you see that the total derivative of this Hamiltonian would be equals to the partial derivative of the Hamiltonian with respect to time. Okay. So one thing I want to remind you is that in the chapter 2, part 3, when I was talking about the conservation law, right? So you remember that the last case I was talking about is the conservation of energy, right? So and then I was showing you that the time translational symmetry will give us conservation of energy, right? And then at that time, right, so we were considering the total derivative of this Lagrangian with respect to time. And then after the rearrangement, you may remember that the partial derivative of this Lagrangian with respect to time is equal to the total derivative of this whole thing here. Okay. And that thing is in fact the Hamiltonian. Okay, so that's, and that time I just basically very quickly told you that the Hamiltonian is essentially is the total energy of the system, right? So, but I did not say much more details. Okay, so but today we will. Okay, so the Hamiltonian, okay, so it's something that you have seen a few chapters earlier. Okay, so just a reminder over here. Okay, so now again, I want to remind you about the difference between the partial derivative and the total derivative. Okay, so because now that I have this partial and total, it might looks a bit confusing. Okay, so where do we have this total derivative and where do we have this partial derivative? So again, if I have a Lagrangian, okay, so that is depends on this Q and Q dot only. Okay, so then the partial L partial T would be 0. Okay. So let me give you a real example. Okay, so let's say L again. Let me use a simple harmonic oscillator. Right, just this. Okay. So this one does not depend on time explicitly, right? So, but you might argue that well, L is in fact is also, it should be a function of time, right? So because this x is a function of time, and this x dot is also a function of time. Okay. However, right? So the rules is that if you write down the Lagrangian, okay, so if you can write it as, right, so the kinetic and the potential energy like this, right? So then you are basically going to express them in terms of the position and velocity, right? So but not explicitly on time. Okay. So although, okay, so this depends on time and this depends on time, right? So we know that, but we don't say that this Lagrangian, okay, so depends on time explicitly. Okay, so that's one thing to remember. Okay. Then when can I say that it depends on time explicitly? So I think previously I gave you an example, like if K itself, the spring constant itself is changing with time, right? So then we have to write this K as a function of time, KT. So then in that case, right, so we can then say that the Lagrangian depends on time explicitly. Okay. So now this L, right? So and now if this is depends on time, does not depend on time explicitly, right? So then we'll say that this partial L partial T is 0. And that means partial H partial T is also 0. Okay. And if partial H partial T is 0, then this dH dt has to be 0. Okay. So that's not the case for Lagrangian. Okay, so in this case, right, so Lagrangian will be equal to 0. So well, I'm just keeping a constant K now. So in this case, what about dL dt? Is dL dt 0 or what? So here, okay, so now we all agree that partial L partial T is 0. What about dL dt? Look at this. Is dL dt 0 or not? So dL dt is not 0. Okay. So why is that? So just think of, go back to the original definition of total derivative. Okay, so just write it out. So the original definition of total derivative is like this. Okay. Basically using Kang rule, right? Right. So this is the definition of total derivative. Okay, so remember. So now this partial L partial T is 0. Okay, but what about these two terms? Right. So what is this? This partial L partial X is minus Kx. Right, and then with the X dot over here. And what about partial L partial X dot? Is the Mx dot here, right, times X double dot. Okay. So if you work them out, so what is X and X dot? Okay. So if you actually solve the equation of motion, you'll be able to figure out X and X dot, right? So what is X? X would be something like this: A cosine omega t, right? Simple harmonic oscillator, right? So and where omega is given by square root of K divided by M. Okay, so from that, you can work out X dot, you can work out X double dot, right? So you can try to find the the sum of the two terms, and you'll find something that with the sine, cosine, and they don't actually get to 0 all the time. Okay, so therefore, this total derivative of a function with respect to time being equals to the partial derivative of the same function with respect to time is, right, in general not true. But for Hamiltonian, okay, so this is true. This is easy to understand, even you don't do the partial derivatives, right? So because if you think about the energy, right? So the Lagrangian of the harmonic oscillator, right? So at different time, right? So of course they would be different, right? So you understand that for the let me draw the P and KE, right? So the PE of the, if the PE of the simple harmonic oscillator looks something like this, then the KE, okay, so this is PE, then the KE would look something like this, right? So I think you have learned this before, right? So now if you do this blue curve minus the green curve, well, clearly you see that won't give you a constant. Right? So on the other hand, if it is KE plus PE, right, so you know that they add up to a constant. Okay. So then be careful about the difference between partial derivative and total derivative. So now, when we talk about the conservation of a quantity, okay, so we are always saying that the total derivative of that quantity being 0, okay, at all time. Okay. So therefore, from here, we'll say that, okay, so if L does not depend on time explicitly, that means partial L, partial T is 0. That means partial H, partial T is 0. And that means dH dt is 0. So that means if L does not depend on time explicitly, then H is conserved. Okay. But if partial L, partial T is equal to 0, so L does not depend on time explicitly, that does not imply that the Lagrangian is conserved. Okay, so that implies that the Hamiltonian is conserved. Okay, so then in the next part of the chapter, okay, I'll go to talk about the relation, okay, so between the Hamiltonian and the energy. I'll show you that in most cases that we consider, right, so Hamiltonian is the total energy of the system. Okay, so this is just a slide to summarize, okay, so the equations, okay, so that we just have learned. Okay, so before I go to talk about the physical meaning of the Hamiltonian, which is the total energy, right? So in most of the cases, as I just said, I want to give you one more remark about the derivation of the Hamilton's equation of motion. Okay. So how did we derive the Hamilton's equations of motion? We rely on the Legendre transform procedure for the Lagrangian, and we also need the Lagrange equations. Okay. And how did we get the Lagrange equations? So ultimately, it is from the what we call the principle of least action, or the variational principle, or sometimes we call it the Hamilton's principle. I'll just call this a principle of least action. Okay. So from the principle of least action, right? So we have this, right? So right. So because of principle of least action, we have the Lagrange equations, right? So and then we do Lagrange transform from the Lagrangian, get to Hamiltonian, and then we get to this set of equations, right? So together of Lagrange equation, finally, we get to the pairs of the Hamilton's equation. Okay. So that is to say, in these procedures, the Hamilton's equations are not directly obtained from the principle of least action, right? So it is indirectly obtained from the principle of least action, I would say, right? So because the principle of least action in this case gives us the Lagrange equation, that's it. Right? So here, I would like to show you that these pairs of Hamilton's equations can be directly obtained from the principle of least action. Okay. So what it means is the following. Okay, so is that what we had before. Okay, what we had before is this one. So this is the principle, the version of the principle of least action that we used. Okay. So now, okay, so we define this Hamiltonian function, okay, as this. Right. So then that means this is equivalent to this, right? So these two should be equivalent, but because I'm just rewriting the L, okay? So because H is equals to this sum minus L, that's why this L is equals to this sum minus H. Okay. So this is where we start at. Okay. So for those of you who don't remember the delta notation, okay, so just recall that in chapter 1, well, just the last two slides of the chapter 1, okay, so I have introduced this so-called the delta notation. Okay, so when we try to vary, okay, so the path that we consider. Okay. So okay, so but let me put it this way. So the derivation that I'm going to talk about, okay, so this one, for sure won't be appear in the exam or homework. Okay, so I would just treat it as an optional part. Okay, so but for those of you who want to see how it works, okay, so you can try to follow this. Okay, but if you are not so familiar with this delta notation from chapter 1, okay, so that's still okay. But still, I want you to get the idea. Okay, so even you are not able to follow the entire procedure, at the end, I want you to be able to get the idea that the Hamilton's equations themselves, okay, so can be directly obtained from the principle of least action. Okay. Without knowing the Lagrange equation. Okay, without knowing the Lagrange equation. Okay. So how do we get the Lagrange equation? The Lagrange equation, it comes from this variational calculation. Right. So but now we don't start with this, we start with this. You see that this integral, okay, so is containing Hamiltonian, okay, instead of the Lagrangian. Okay. Okay. So here, okay, so I don't think I will just follow all the steps very slowly or in details. Okay, so but essentially, right, so just remember the rules of using this delta notation, that if a delta notation outside, you can move it inside. Okay, so and then the operation for this delta notation basically follows the total differential, right? So you can see that this delta notation, I put it for the two terms individually, and then here I'm going to use product rule to give me these two terms, right? So and then here, because h depends on this p and q, okay, so that's why I have these two terms coming out, okay. And then one more property here I used. See, the first term here is that the derivatives symbol and the delta symbol, the order can be interchanged. Okay, so from here to here, you can see that I interchange the order between the time derivative and the delta. So, and next step, using the integration by parts, I'm able to get rid of this ddt symbol. Okay, so in front of this delta q, okay, and then give me this. So then the strategy is that, so for the Lagrangian, if you still remember, okay, so you might want to try this procedure by yourself with Lagrangian first. Okay, so you will see that if you do this variational calculation for the Lagrangian procedure, right, so you will have this term with delta q, and then this term with delta q dot, okay, and then using integration by part, right, so you should be able to also make this delta q dot term, okay, so becomes delta q term, right? So that is at the end, right? So when you do this variation for this integral for Lagrangian, at the end you get something like this. Right, so after all the manipulations, all the terms comes with this delta q, and then what's left in front is the Lagrange equation, right? So here, the difference is that you can see that now I don't just have delta q, okay? So I also have delta p. So when you do it for Lagrangian, you have delta q and delta q dot, but they all can be converted to the terms with delta q. But here I have delta q and delta p, okay? And then we are not going to try to mix all the terms, okay, so to go with delta q, okay. So we allow that the fact that some of them will be with delta q and some other terms will be with delta p, okay. So that is, okay, so at the end, you have these two groups of terms. The first group comes with delta p. The second group, okay, so comes with delta q. Okay. And then when we are doing this, basically our thinking is that we treat delta p and delta q to be two independent variations. Okay. So in the case of Lagrangian, so when you have this delta q and delta q dot, right, so we don't treat this delta q and delta q dot to be independent variation. Okay, so because this delta q dot can be converted to the terms of delta q. Okay, so here delta p, delta q, we treat them as independent variation. And if that's the case, then because this whole thing has to be 0, and these two are independent, so that's why these terms in this first bracket has to be 0, and also this bracket has to be 0. They have to be both zeros, okay, so together. Then you get these two equations, okay, and which are the Hamilton's equations of motion. Okay. Hamilton's equation of motion is here. Okay. So that is, here's the summary. Okay. If you do this, delta Q dot dependent. But here, we really treat this delta Q and delta P to be independent variation. So, but here you might have a question in mind, is that why can we treat this delta P and delta Q to be independent? That is, why can we treat them as independent variables, right? So because, well, we understand that, well, just consider one-dimensional motion, one-dimension linear motion. You know that P is just mx, right? So this is what we've learned before, right? So momentum just, oh, sorry, mx dot, right? So then how can we say that x and p are independent, right? So they are related like this. How can we say that they're independent? Okay. But just like here we don't say that q and q dot are independent, right? We say that they are dependent, right? That makes sense, right? But here I'm telling you that, right? So p and x are independent. So the idea is the follows, okay, is that when we do the variations with the Lagrangian, right? So remember that we have a picture like this, right? Just one-dimensional case, right? So the starting point and the ending point, and then we are trying to look for the path that gives us the minimum value for the integral. And there are many possible paths, right? So infinitely many, essentially. And each path, right? So I call this x as a function of time. And now, once you pick a particular path, that means you pick a particular form of x as a function of time, then you immediately know x dot as a function of time, right? Because just taking derivatives, right? So that means that no matter what path you pick, right? So you cannot tell me that x and x dot are independent, actually. So that's not true. However, here the idea is the following, okay, is that I'm going to draw a picture like this. So here I am drawing actually a three-dimensional plot. Okay, like this. And then again, I do have a one starting point and a one ending point. But this is a three-dimensional plot. Okay. Now, again, you are allowed to pick your path. Okay, so but okay, I am not able to draw it very nicely, but you just imagine that now that the path that you pick, okay, so are living in this three-dimensional space. Okay. So, and the path you pick here, okay, just on this plane. Okay. And then amongst all the paths you can choose, okay, you'll be able to see that for many of them, P does not necessarily have to follow this relation. Okay, so if indeed I give you 2 points and then I allow you to draw any arbitrary path in this space, you will find that, okay, so this P equals mx dot not necessarily true. It really depends on how you draw them. So that is the idea, is that when we work with this, we pretend that we don't know anything about, we learn from the Newtonian mechanics, right? So that is, you don't even know this. You don't even know P equals mx dot, okay? You don't know any about this. And then you basically, you just have the two variables here. And then you are going to do your variational analysis. And then at the end of the day, you find that to minimize this integral, right? So you will have to satisfy this one being 0 and this one being 0. Okay. And then from these two equations, okay, you will be able to find that P equals mx dot. So how? Right, so just look at this equation over here. Right, so this one basically tell me x dot equals partial h partial p. Okay. And what is h? So h would be written as something like this. Right. And partial h partial p would be p divided by m. Okay. So then from here, you finally realize that p is equals to mx dot. Okay. So that's how it is different. Okay, so from the Lagrangian. Okay. And then I hope you see the idea why at this point. Okay, so when we do the variation analysis, we are treating P and Q to be independent variation, because at that point you don't even know that P is equals to mx dot. Okay, I think okay, so we should take a break. Let's take a break for 10 minutes. Okay, we'll come back at 12:40. Okay, so let's continue. As I said, okay, so if you don't really follow the details of the derivation that I just shown, okay, so that's all right. But at the very least, okay, so these are the information that we are going to use. Okay, so you have to at least, okay, remember that the Hamiltonian is defined by this equation here. Okay, and then the Hamilton's equation of motion are always given by these pairs. Okay, so sometimes we call them the canonical equations of motion. Okay, and also, okay, so the time derivative of the Hamiltonian has these two nice properties. Okay. Okay, so next I'm going to move on to part B. Okay, so right now we don't really have much sense or feelings about this Hamiltonian function, right? So although I told you multiple times that this Hamiltonian is in fact the energy, right? So but at the very least, if you just look at the definition of Hamiltonian here, it might not be so transparent for you that, oh yeah, this is the energy of the system. Okay. So then, this is what we are going to do next. Okay, so to convince ourselves that, yes, in most cases that we consider, the Hamiltonian is the total energy of the system. Okay, so then let's go. So here, okay, so let me tell you the results first, and then I will show you why they are true. Okay, that right. So I have this Hamiltonian defined like this. Okay, so we'll see that the Hamiltonian will be equals to the energy, the total energy of the system, potential energy plus kinetic energy. Okay, if the following conditions are satisfied. Okay, let me go to the second one first, because the second one is something that you don't need to worry about really, at least in this chapter, is that the potential energy U is velocity independent. What does it mean? That means potential energy is not a function of velocity, but well that's of course the case, you will say, right? So because the potential energy that we have seen, right? So like this, right? So like this, 1/r mgh, all that. Of course, potential energies are not velocity dependent, right? So they only depend on position, right? So that's true for all the cases that we have considered, right? So later in this course, I will give you example on potential energy being depend on velocity, but that would be some optional content. But anyway, so what I'm telling you is that, yes, no need to worry about condition 2. Okay, so we will just be focusing on all this potential energy, and of course they are velocity independent, right? So, and this condition 2 means that this partial U partial Q dot is 0. Just take it for granted for now. Okay, so no need to worry about condition 2. So what about the first one? The first condition is that the equations of the transformation connecting the rectangular or the Cartesian coordinate and the generalized coordinate are independent of time. What does it mean? So first, it means that if you use Cartesian coordinates or rectangular coordinates, that means you are going to use x, y, z. Right? So if you are going to use x, y, z to express your Hamiltonian, it is guaranteed that this whole thing is total energy. I think I've shown that in chapter 2, but I will do it again. Okay, so I'll show that to you again. So now, if you use, the question is, what about other coordinate systems? Right, so for example, if I use polar coordinate system, that is right. So if you use polar coordinate system to express your Hamiltonian, okay, so will that also give you total energy? Well, so that's the kind of the questions that we are going to address. And it turns out that yes, right? So what it says here, as long as the transformation between the coordinates that you are going to use and the Cartesian coordinates are time independent, then that's okay. Right, so you can see that the transformation formula does not depend on time at all. Right, so and well, so that is right. So in general, right, so I have this x, y, z, do some transformation to becomes Q1, Q2, Q3, right? So if this transformation is independent of time, then we are fine. Okay, so let's do examples. Okay, so one particle systems in a velocity independent potential. Start with the Cartesian coordinates. This is the key KE that I have, right? I just worry about 2 dimensions. Okay, so same thing for 3 dimensions. Okay, so for 2 dimensions, this is the kinetic energy. And then what do we do? Okay, so I'm going to find the momentum first, right? So because I'm going to express the Hamiltonian, right? So the Hamiltonian has to be expressed in terms of the P. Okay, so this is Px, Py. Okay, so everything's okay. And then now I'm going to consider this sum, right? So because the Hamiltonian, I need to consider this sum. So this sum is given by Px x dot plus Pyy dot. And that would be, right? So using these two relations here, it would be m x dot square plus m y dot square. And that is 2 times the kinetic energy. Okay. So if it's 2 times the kinetic energy, then this sum minus the Lagrangian will be 2t, 2 times the kinetic energy minus t minus u. That would be t plus u. And that would be the total energy of the system. Okay. So that is to say, so let me make this clear here, is that as long as we find that this sum is equals to 2 times kinetic energy, then we can safely say that this Hamiltonian is the total energy, right? So because 2t minus L would be t plus u. Okay, right? So that's the thing that we are concerned about, to test whether this sum is equal to the 2 times the kinetic energy. And for the case of the Cartesian coordinates, we show that it is. Okay. So next, let's use polar coordinates. Right. So I want to know that in this case, whether the sum will again give me 2 times the kinetic energy. Okay. So here, right. So again, this time I need to find out the generalized momenta PR and P theta, which is given here. Okay. And then the sum. So this time the sum is PR R dot plus P theta theta dot. Right. So instead of PXX dot plus PYY dot. And here you will see that the PR R dot is actually M R dot times R dot. And then the second one, okay, I have a typo here, just one factor of M. Okay. The second one is M R square theta dot theta dot. And you again realize that this sum is equals to 2 times the kinetic energy. Okay. So then again, we are good. Right, so the Hamiltonian will be equals to the total energy. So let me try one more case with other coordinates. So this time I'm going to use this coordinate pairs UV. Okay, so instead of this XY. And this UV and XY are related by these two equations. So you can imagine that this is some kind of a linear transformation. Okay, so from XY to UV. Okay. Well, although we don't really use these pair of coordinates a lot. Okay, so I don't have an example that use these two coordinates. Okay, so I don't see why this is more convenient than using XY. Okay, so but anyway, this is a choice that we can have, right? So I can call this UV as a pair of generalized coordinates anyway. Okay, so in this case, what about the kinetic energy? Okay, so kinetic energy in the XY coordinate is written like this, right? So I want to convert it in terms of U and V, right? So then what I need to do is just this, right? So this is U equals X, that means U dot equals X dot, right? So V equals X plus Y, that means Y dot equals V dot minus X dot. and x dot is just u dot, right? So this is v dot minus u dot, right? So then here you can see that this m u dot square plus v dot minus u dot all square. Okay. And then if I just expand it out, this is what I get. Okay. So it looks weird, right? So it does not just contains the square term, it also contains a term which is composed of the product of the two coordinates, which we call the cross terms. But anyway, this is what it is. And if I just here, right, so try to find again the generalized coordinates, right? So for u and v, then this is what we get. Okay, looks funny. Okay, so but by definition, they are like this. So now consider the sum again, right? So this time, this sum, right? So it would be pu u dot plus pv v dot, and then I just put all these formulas down here, and you again find that this whole thing, which is this thing, is equals to 2 times the kinetic energy. Okay, that means again we are fine. Hamiltonian expressed in uv also gives the total energy. Okay, so it doesn't matter, right? So exactly what coordinates we choose, right? So and as long as, right, so you can see the common feature, right? So is that the transformations does not depend on time. Okay. So now let me give you an example that the transformation depends on time. This one. So I think you might have seen this before. This is essentially you can call this the Galileo transformation, right? So what we have is here, right? So the black coordinate system, right? So the xy, right? There's a coordinate system at rest, right? So and then you have a car, okay, or box, okay, so moving at a constant velocity v naught, and then in that car or in that box there is a particle here. Okay, so I did not say whether the particle is at rest with respect to the car or not, but it doesn't matter. Okay, in general, the particle can be just sitting in the car, or it can actually be moving or jumping. It doesn't matter. But this is the system that we set up. Okay, and now the x prime y prime that I define, okay, would be indicated over here. Okay, you can see that, right? So the x prime is the distance between the backside of the car and the particle, right? And the x is the distance between of this particle and this fixed point here. Okay. So therefore, right, so this x prime and x is related by this equation here. Okay, so for y and y prime, okay, so they are just measured from the bottom here. So y and y prime are just the same. Okay, again, now I want to express the kinetic energy. Okay. So notice that I'm always talking about an observer who is standing over here at rest. Okay, so I'm not really considering, although I have 2 pairs of coordinates, but I'm not really considering an observer standing on the car. Okay, I'm still considering the observer standing at rest at this O. Okay, so now if I consider the kinetic energy, right? So this is what we have. So if we use the xy, right? So this is it. Now, if I want to express the kinetic energy, right? So in terms of this x prime and y prime, then this is what we have to write down. Okay, so because from here we have x equals x prime plus v naught t. And this is just y equals y prime. So that means x dot equals x prime dot plus v naught. And y dot is just y prime dot. Right. So that's why this x dot term becomes this term. Right. This y dot term becomes this term. So now if you just again expand the terms out, then this is what you have. Okay. So this time, right? So I'm always following the same definition for the generalized momenta, right? So px prime and py prime. Okay. So now let's look at the sum. Right, the sum of p q dot. So carefully look at the calculations here. This time, you see that this is not 2 times this. Okay. I have the x dot square term. I have the y dot square term. Right. So these two. But you can see that these terms is different from these two terms. So this time, see an example that the Hamiltonian is not equal to the total energy of the system. Okay. And because this time the transformation between the Cartesian coordinates and the generalized coordinates that we use contains a time-dependent term here. Okay. And then also you can notice that in this case we have the term that is constant and a linear term here. But in the previous case, right, so we always have the coordinate dot square terms, or the product of the two coordinates. So they are all what we call the quadratic terms, right? So same thing here, always comes with the square. Right, so here we have the terms that does not depend on the coordinate square, right? And this one also not square. It's just a linear term in the coordinate dot. Okay. So in general, okay, so for a system, does not have to be just one particle, it can be many particles. The kinetic energy, well, should be able to express as this form. Okay. The quadratic terms, the linear terms, and the so-called other terms. Okay, so that does not contain any q dot. Okay. Okay, here, sorry, I'm missing a dot here. So, and you can see that for case 1 to 3, so that is except this case, the kinetic energy, right, only has the quadratic term. Right, so but for case 4, the time-dependent case, these two terms comes out. Okay. And it is because these two terms, okay, so we don't have the sum being equal to 2 times the kinetic energy. Okay. So it can be shown that mathematically, okay, so if this kinetic energy only contains the quadratic term, then this sum will be equal to the 2 times the kinetic energy. So skip the proof. Okay, for now, okay, so you can refer to the textbook. Okay. Okay, but now I think you are convinced that, okay, so in most cases, right, so the Hamiltonian is indeed equals to the total energy of the system. Okay. So with that in mind, okay, so I think is a bit more comfortable, okay, so to work with this. Okay. All right. So now let's try to use Hamiltonian and Hamilton's equations, okay, so to actually solve mechanics problem. Okay. So the problems that we are going to look at won't be new. Okay, so we are just going to consider the same kind of mechanics problem that you have probably seen already. Okay, so but we are just going to use this Hamiltonian's method. So what is the procedures of that? Right. So the procedure is that we still need to start with the Lagrangian. Okay, so in principle, we still need to do that, right? Because the Hamiltonian has to be obtained from the Lagrangian. So right, so the first again is to select generalized coordinates, construct Lagrangian. Okay, so and then from there you find the generalized momenta by this definition, and then you will be able to derive the Hamiltonian. So using this formula, right? So, but one thing to always remind yourself is that the Hamiltonian has to be expressed in terms of Q and P. Okay, so not Q and Q dot. Okay, has to be Q and P. Okay. And then after that, right? So you use these pairs of Hamilton's equation. Right, so these pairs of Hamilton's equations are the equations of motions for your system. Okay. So, of course, right? So sometimes we can skip the steps, right? So because physically we now understand the Hamiltonian, right? So in most of our cases, will be just total energy, right? So with that in mind, right? So you might not necessarily just do the Lagrangian first and then use this formula, right? So you can just start with, you can simply start with H equals T plus U. Okay, so that's also okay. You can do that, skipping the step of Lagrangian. However, always remind yourself that when we express the kinetic energy, do it in terms of P, not Q dot. Okay, so then let's try to see how it works in different coordinate systems. Okay, so right, so this I think I don't have to repeat again. Okay, so you familiar with this already, and then Hamiltonian like this, and then Hamilton's equation like this. So as I said, right, so if you, with the physical understanding in mind, right, so you can, with your first step, just write down this, right? Because this is KE, this is PE. So look at the Hamilton's equation now. Okay, so this x dot equals px divided by m, and so on. Okay, so this px dot equals minus d u dx and so on. Right, so everything are not surprising, right? So they are just consistent with what we learned before, right? So what is this minus partial u partial x? Force, right? So x component of the force, right? Similarly, y component of the force, right? So therefore, let's just look at the x component, for example, right here. So x dot equals px divided by m. Px dot equals partial u partial x, right? So practically, when you solve them, right? So at the end of the day, you are going to combine these two equations together. Right? So what you do is that you take the derivative for the first equation. So x double dot equals dx dot divided by m. Right? So and let's substitute into the second equation. What do you get? M x double dot equals minus partial u partial x. Right? So Newton's equation here. So next, let me see if I have the picture here. The cylindrical coordinates and the spherical coordinates. Okay, I think I wanted to put a picture over here to remind you of using the other coordinate system. Okay, but I don't have that. Okay, so let me try to find it from my old notes. So essentially from 2051. Okay, so if you have taken that course in the last semester, you might still remember that. So this is the differential element for the vectors in the spherical coordinate, first of all. Okay, let me try to see if I can get the picture. Okay, over here. Right, so we call what we've learned about the differential elements in the spherical coordinates. Okay, so and I'll also do the cylindrical coordinates. Okay. So the dr is the differential element. Okay, so vector in the spherical coordinates. Right. So why do I want to talk about this? Because I want to talk about the kinetic energy in the spherical coordinate. So that means I need to express the velocity in spherical coordinate. So that means I need the dr dt, or at least the magnitude of dr dt squared in the spherical coordinate. Okay, so the dr r hat, right? So what does that mean? So this is the dr, right? So that means, right? So if I am going to have a vector function, right? So in this spherical coordinates, and if I'm going to have this vector function, right? So in this spherical coordinates, and if I'm going to change the r variable a little bit, then this vector function, right? So will change by this amount. Right? So that is to say, if your particle initially is here, and if you change the r value a little bit, so that means that your particle will move to here. Right? So if you keep the theta and the phi variable fixed. Right? So on the other hand, right? So if you are going to change the theta value of your vector function, then your particle, right, so will move from here to here, right? So by this much amount. So what is this length? This length is r d theta. So similarly, if you change it, change the phi value a little bit, right? So then you will move like this by this amount. So this would be r sine theta d phi. So therefore, right, so if you want to consider the velocity, right, so then you just need to do the dr dt. Right, so dr dt would be this. Okay. So therefore, if you want to find the kinetic energy, right, so you want the v square. So, or the magnitude square, this, right? So that would be equals to dr dt square plus r square d theta dt square plus r square sine square theta d phi dt square. Right. So this is how you express the v square in the spherical coordinates. Right. So that's why if I write down the Lagrangian, this is what I have. Right. So for the kinetic energy, this is the potential energy. Then using the same definition, right? So PR, P theta, P phi, like that. Okay, and then Hamiltonian, right? So then this is what we have. Okay. So again, it's okay for you to start from just this step. If you remember, okay, so this expression is the kinetic energy. Okay. Okay, so then again, Hamilton's equations of motion. Okay, so r dot theta dot phi dot, right? So PR dot P theta dot P phi dot. So at the end, okay, so you see that these equations, of course, will be the same as what we could obtain from Newton's equations or Lagrange equation. Okay. Oh, okay. My pictures are actually here. Okay. Yes. Okay. So then, and then the next one, I'll just finish it very quickly, right? So it's the cylindrical coordinates, right? So for the cylindrical coordinates, as again, if your particle is over here, and if you change the rho variable a little bit, then your particle will go from here to here in this direction, right? And then similarly, you just change the phi variable a little bit, just go from here to here. Okay, and then I just testing the z variable a little bit. Your particles go from here up here, right? So then again, you are going to just do the dr dt, right? So to get to the velocity, okay, and then from that, you should be able to find that, right? So the kinetic energy looks like this. Okay, same procedures here. Okay, so no need to repeat again. And then Hamiltonians written like this. And these are the canonical equations of motion. Okay. Okay, so next time we'll start with some examples. Okay, so with some mechanical system. Okay. So and that's it for today.